events here bi-monthly for the past 2 or 3 years, and I've been lucky to meet a lot of awesome people, and we've had a lot of people join up to help organize, some of which are in the audience. So we kind of exist to just bring the robotics community together in Tokyo, and hopefully beyond that for anybody visiting. So yeah, please look into us on LinkedIn and Meetup, and if you have any ideas for future sessions, we're happy to collaborate. Yeah, we love robots. So tonight, we are tackling a subject, it makes it sound very serious. We've done Robotics X, video games, healthcare, children, education, different, we have a theme each time. And I was very lucky to receive a message from, surprisingly, the sister of the head of that robotics group that I was a part of in Silicon Valley. She is Australian, and her sister is now the director of the Robotics Institute at University of New South Wales, UNSW Sydney. And so she said, hey, we have a great group of researchers coming to Japan. And I said, let's have an event, and the timing worked out perfectly. So I'd like to welcome our guests from Australia, from UNSW, and I'm going to let them take it away with a brief self-introductions. Jiko Shokai.
Jiko Shokai.
Hi.
So, hi, thank you very much for having us. We are from UNSW Sydney. We're from the School of Mechanical and Manufacturing Engineering. In terms of the university, most of the robotics activities within that part of the university, mechanical and engineering school. In terms of the university, we are one of the best universities in Australia. We're normally ranked number 19 or 20 in the world, and we have broad range of activities. Some of those are robotics. You'll hear about that today, about robotics and mechatronics. But we also have, obviously, among the engineering faculty, lots of different work in sound and vibration and so on. As Mike said, we have a new AI institute led by Dr. Sue Kay. She is excellent and very good at putting people together, which is why we're here and why we got in contact in the first place. So the AI Institute is a cross-disciplinary virtual institute where we have 300 staff or so who all combine to try to solve or think about the benefits and problems of AI. They are faculty members from engineering, computer science, but also arts and design, economics, and law. And the intention there is to try and form this brains trust that we can talk about AI in an open way. So in terms of the mechanical school, like I said, we represent most of the people who do robotics and mechatronics. In particular, my field is underwater robotics. People often ask me why I chose underwater robotics, and I say that it's just because it's very, very hard. Everything underwater is harder than it is above ground. So my research at the moment is to do with reinforcement learning and a little bit of AI to do with understanding the scene that is around the robot and how it can navigate, and trying to deploy that into what we call edge devices, devices that are not connected necessarily but can autonomously undertake some tasks by themselves, which again is very difficult underwater because sensing is very hard and computation is very expensive. So that's where my work focuses, and I'll just, we'll kind of do quick Jiko Shokai introductions of the work that we're doing one by one. So over to Shiyang.
Thank you for having us. My name is Shiyang. Good evening, everyone. I'm currently with School of Mechanical Manufacturing Engineering at UNSW. Just gonna give very layman quick introduction to my work. I think that's probably this way. 30 seconds, right? All right. How many of you have watched the movie Terminator 2? Terminator? Good. So all of you know the T-1000 liquid metal Terminator, right? That's what I'm working on. So yeah, that's what I'm working on. It's just basically just new materials, smart materials, how make a control the surface tension, change the stiffness, change the phase of the liquid metal, and make it into a robotic system. So just remember, I'm working on Terminator. That's it. But I'm not gonna destroy the world. I'm not gonna kill you.
Famous last words.
Yeah. Okay.
They all say this.
Now I'll just hand it over to Leo.
All right. Good evening, everyone. I'm Leo. I'm currently an associate professor at UNSW. We are also from the same school. So my background is also in robotics. And in particular, my research focuses on making people's life healthier So how? Well, in two aspects. First is to develop intelligent surgical robots to make surgery easier and safer, help surgeons to perform surgery better and bring benefits to patients. And in particularly, we design new novel robotic systems, and we call them snake-like robots. So you can imagine how snake navigate through environment. We mimic this behavior. We design flexible robots that's at a scale of several millimeters that can be inserted into patient's body, bypass some critical tissues, and reach the target and do some manipulation and operation. Another aspect is to develop wearable robots for rehabilitation. And in particular, many of you may have seen exoskeletons where people can wear robotic device to walk or do some daily tasks. What we are doing is developing exosuit. So instead of exoskeleton, which utilize rigid frames, we want to embed the novel materials into people's clothes so that it's compactor, more wearable, but still can help people function better. So that's me. Thank you.
All right. So good evening, everyone. My name is Phan. I'm an associate professor at UNSW, and actually I live in Tokyo, Japan for a while. I did my undergrad and a master at University of Tokyo quite many years ago. So my friends over here working on robot, and we know that we need sensor to control robot. So my research lab working on sensor development for understanding human-machine interaction, like tactile sensor that can be used for grip control. And we also develop miniaturized sensor that can be integrated into Leo's snake-like robot, so that the sensor can do impedance sensing for dysfunctional tissue detection, and also can apply RF ablation to remove the dysfunctional tissue. And beyond robotic application, we also develop other type of sensor that can be used for home-based health monitoring. Like an example is a wearable acoustic sensor that can replace the stethoscope. We know that whenever we go to a clinic center or hospital, we always see medical doctor wearing a stethoscope, right? And it's a very simple way to diagnose heart or lung disease, but the patient always need to go there, and it's not very relevant for those who live in remote area. And people normally go to hospital when the disease is really severe. So we want to develop something that really thin and sharp, like smaller than your thumb, thinner like 3 millimeter, that have all the components, sensor, Bluetooth, battery, and can be easily attached onto your chest and continuously hear your heart sound and can tell if you have symptoms at very early stage. All right, thank you.
Thank you. Thank you very much. All of that is fascinating, if not terrifying, T1000. I have many questions specifically for each of you to your research, which I will probably save because it would take too much time. Instead, what I would like to focus on, as we discussed previously, is Australia. You mentioned previously that there are particular challenges that are ripe for robotics, specifically in Australia, and I'm wondering, A, what those are, and B, how applicable they are to, say, Japan, which we have our own, aging society and other, issues that are ripe for physical embodied, robots, and the rest of the world. So, do you have any thoughts on that, Will?
Yes, I do. So Australia is surrounded by sea, unsurprisingly, similar to Japan. And the way that Australia gets all of its internet is through fiber optic cables. There's about 16 or 17 of them that make landfall in Australia. And unsurprisingly, they're very crucial to the infrastructure of Australia. And so we need to know where they are and their condition and be able to monitor them. And it's well known that underwater diving, commercial diving, roughly has a fatality rate of about every 2 to 4 people per 10,000 people die every year doing commercial diving. So it's a highly dangerous activity. And so normally when we're talking about robotics, we try to get rid of dull, dirty, or dangerous tasks. And so this counts as a dangerous task. So for underwater robotics specifically, in my area, in sending down robots to try and do this infrastructure assessment, monitoring, and understanding what's going on is far safer than having to send down commercial divers. And so part of this longevity in trying to understand how they are aging and monitoring them in real time requires underwater robotics to do that. So I think there's very clear parallels with Japan. Japan also, as an island, also has fiber optic cables connecting across the islands and also, I presume, across the Pacific. So trying to maintain this underwater infrastructure, ports and so on are also super important, again, for island nations. So trying to ensure that all this infrastructure is kept up to date and safe is crucial, and trying to prevent divers dying is really key, I think. So that's where my research comes in, trying to stop these commercial divers losing their lives for trying to figure out what's happening with a fiber optic cable, is what I would say.
Nice. And where would you say that you are now, your research in terms of its maturity in either replacing or assisting divers? And then also, what is the reaction of the diving community say? Are they accepting of this, or do they push back against it? Like, our jobs are going to be replaced as divers.
I think there's always, I'll answer the last question first. Sure. So there's always a tension with people who perceive that they are being replaced by robots. However, in this case, with that job that's so dangerous, I think they understand that this is a job. And that and on top of that, there are jobs that we can do with these robots that can't be done with humans. So some of these cables are off the continental shelf, so they're very, very deep, and we wouldn't send divers down there. It's not safe. So it's to try and work with them, as well as trying to stop them having to lose their lives doing this task. So I think they understand that in general. In terms of my research, as I said, underwater robotics is really, really hard, it turns out. So we're still working on some of the kinks, but we have got a project at the moment working with an industry partner to look at and monitor underwater piles, so things that hold up wharves, and understand when they're cracking and why, and 3D modeling of those to try and help them do I don't like the word, but digital twin of those to help them understand how things age underwater, the infrastructure.
That's great. Thank you.
Thank you.
So moving on. Yeah, maybe specific to Australia. So materials and specifically liquid robots sounds amazing.
Yeah, firstly, of course, when you're working with conventional robotic systems, you always think about rigid actuators, rigid end effectors, everything's conventional, but I'm trying to make things unconventional. So just make everything out of liquid or soft materials. So all the way from the actuators to the end effectors, everything's soft. From the scientific perspective, it's quite interesting because no one has done that before. I've been working on this since my PhD, has been 15 years. Maybe less than that, but I think it's quite interesting and intriguing because it's curiosity driven. Can we make everything out of liquid? That's the first thing you want to ask. But in terms of application perspective, because I'm more work with the biologists or biological samples. Whenever you want to handle dedicated objects like tissues, embryos, or for example, a large organism like jellyfish or earthworm, yeah, conventional robotic system is a little bit tricky because it's not efficient to grip it, and sometimes you can kill or damage the biological sample. That's the reason why it is necessary to use extremely soft materials to complete the task efficiently and rapidly. And another important thing is for very, very tiny things. Maybe have you ever tried? You can easily pick up a hair, but sometimes it's really difficult to release it. Why? Because your hand might become sticky, or some liquid, substantial effect and static charge effect. For tiny things, you can pick them up, but it's impossible to release it. So releasing is another important thing, especially for example in packing industry, in biological sample pick and place tasks. That's the reason why I'm introducing this liquid-based anti-effector. So what I'm doing is actively control substantiation. only liquid method allows you to do it from all the way to highest surface tension among all liquids, all the way drop to zero. By doing this, I'm able to actually pick things up. It doesn't matter what shape it is, what kind of morphology it is, how soft it is, because liquid is liquid, it has no stiffness, right? Just like you have no contact pressure. Pick it up and generate substantial release it quickly, rapidly. Just yeah, that's from the application perspective. It's more for delicate sample, micro, nano size samples, for this kind of extremely soft sample, fragile sample handling. So from fundamental to applications, yes, I think that's one.
So follow-up questions. Sorry.
Anyway, yeah.
So two things. So technically, how do you keep the liquid sort of contained from not itself releasing from itself?
Yeah, a simple term is if you have you played with mercury? Okay, all right. When I was a kid, I played with mercury. Seriously, I was still wondering why I'm still alive anyway.
You have to tell us if you're a police officer.
Yes, like because of the this kind of liquid has extremely high surface tension. That's why it's trying to beat up. It's not gonna spill. Yeah, and it's actually you're able to attach to another metal. So you wet to another metal. That's how you control where it is and where you want it to be. Yeah, that's the easiest way. So it's not gonna spill out. That's where you control it in simple terms.
Got it. And then I'm definitely going to look into this later. Compared to other soft manipulation like canvas, for example, pneumatic robots, or friction jamming, things like that are meant to pick up small, very sensitive parts, or static-based, pickup. What benefits do you see of liquid pickup versus those other very sensitive pickups?
Yeah, I'll just give a few examples. For stiff jamming, you need to have this kind of particles inside the plastic. You can call it balloon, right? So yes, it's okay to pick up this size of big things, but for the smallest thing you can pick up depends on the size of the particles, right? So in terms of micro-sized things, it's pretty tricky to pick it up using. And for electrostatic thing, you have to apply high voltage. Yeah, that's another thing is detrimental to biological sample. That's the reason why liquid sometimes it gives lots of benefit because low voltage, we just apply a maximum 5 volts. Yeah, just to induce oxidation, just like kill the subtension. And yeah, that's the biggest advantage. And we're able to pick up very tiny objects. You can imagine hair or a glass fiber and even some like microparticles. Yeah, so that's the biggest advantage we have.
That's awesome. Do you have a GIF of the Terminator? I'm really glad you started with that. That was a good hook. So next, maybe specifically about Australia, or why would Australia be ripe for your research?
Yeah, right. So Australia currently is facing the aging population issue, right? I guess Japan has the same issue. So when we are having an aging society, one problem is the pressure on the health system is increasing dramatically. Right? You can imagine when people getting older and older, a lot of diseases just come to us, and a lot of more treatment will be needed. Currently in Australia, the health system, I think it's quite in a stringent state. Just to give you an example, my son just recently was advised by the GP he needed to do a small surgery. So we went to the specialist and we were advised to book an appointment. And eventually we were told we need to wait for 1 year for that surgery to be done. Of course, it's not urgent, but that's the reality in Australia. When your surgery isn't urgent, you need to be placed on a long queue list, and they need to prioritize on more urgent surgeries. So to improve this, one solution could be we can develop better instruments for surgeons. So that's why I'm developing surgical robots that can perform so-called minimally invasive surgery. So what is minimally invasive surgery? It's in contrast to the open surgery. In open surgery, the surgeons will do a large open incision, then perform the surgery in an open way. The minimally invasive surgery is like you make a very small incision on the patient's body and insert multiple instruments to perform the operation. So the benefit of this, of course, when you have small incisions, you cause less trauma to the patient because of the surgery itself. It will reduce the recovery time significantly. And also with better instrumentation, surgeons can perform the surgeries with higher resolution, higher precision, and better dexterity. So a lot of new procedures can be done in this way as well. So overall, this will make the surgery faster and reduce the time needed for patients to recover in the hospital. And therefore, we will be able to treat more people with a limited time. So yeah, I guess that's the benefit and impact of my research.
That's great. And just to relate it to something, I actually used to work on minimally invasive surgery in New York. I was an intern at a Peter Walker's lab was his name, but he did minimally invasive surgery for knee cap replacements. So there would be a small incision on each side of the patella, and then you'd go in and kind of replace it, and it was much easier than having your whole knee replaced.
I also work with orthopedic surgeons on knee arthroscopy as well.
That's great. Thank you. Awesome. And then finally, how do you feel your work is particular for Australia?
Right. So maybe I talk about sensors again. In Australia, the mining industry is it's a big deal. So it's I think the second largest industry in Australia, and we have very good relationship with Japan because we import good machine from Hitachi for mining industry. But mining industry also a very dangerous sector. Like we have high rate of injury and so on. So tracking the physical status of mining worker is very important, but we have unmet need in those areas. We don't have technology that can remotely monitor the condition or provide a telehealth service. So that's what I'm doing. We develop sensor that can be distributed to mining worker, continuously measure their physiological status like heart rate, lung sounds, body temperature, and external noise and vibration their body is subjected to. So I think the technology will help close the gap in accessing to advanced technology, advanced healthcare for mining worker, make them healthier, and then minimize the injury in the sector. And in turn, if we can make a lot of money in mining, we will of course import more machine from Japan, and it's the way that support both countries, right? That one example. Another example is monitoring in one side. When we detect the disease, we know how to treat it, right? And a lot of disease like heart disease and lung disease, we not fully understand. And the way we normally model the disease or test drug is to use animal model, like we test on rat. But rat and human are very different. We diverged 75 million, a million years ago. And the heart rate of the rat is 300, and heart rate of human about 70. So 90% of drug work on rat, fail on human. So a lot of disease we don't understand, and a lot of drug fail on humans. So we want to develop technology that speed up the drug discovery process. So what we do is, I think the term humanoid robot is very common to us, right? And then in biology, we have the term organoid. So can you guess what it does? So organoid is artificial organ we use human cell and culture into 3D structure that mimic the functionality of the human real organ. Like we can create lung organoid and heart organoid, and then we can test drug directly on the organoid instead of testing on animal. So we are developing sensor that can measure the contraction at micro scale organoid level. So for each patient, we know this dose of drug is safe for this patient, is optimal for this patient. That's the way we can support drug discovery and screening process.
That's awesome. So yeah, fake organs, terminators. You had mentioned this a little bit at the beginning, but I'm wondering, there is sort of an overall prospectus of, the institute, but in addition to sort of putting sensors on surgical robots, are there very concrete collaborations that are going on between your labs? And can you talk a little bit about those sort of like super projects that might come out of these awesome technologies individually?
I guess I'll start on that one probably. So the AI Institute was developed with that exact thing in mind. There are so many researchers working on AI across UNSW. So there is a large project that's going on between computer science, or in the engineering faculty, and arts and design, looking at how robots interact with humans and how humanoid robots interact with humans. So we come at it, being engineers, we come at it from an engineering perspective. And then working with people from arts and design, they come at it from a very different perspective. They have a very different understanding of what the robot should be, how it affects its surroundings and the people who interact with it. So these projects are really critical for being able to just push robotics forward the next step. So most of the projects, the Institute was only founded a couple of years ago, so we're still kind of building those connections. But the whole idea is to try and bring all those people who are doing robotics and AI together. And I guess the other example I would give is that, so I've said we're in the mechanical engineering school. We physically are located next to the computer science school, but we are in separate buildings. But there is a floor that's sort of a mixed floor where the computer scientists and the engineers are allowed to mix there, you see. So, and on this floor are the people who do robotics like me. My office is up there, and then I am also co-located with the other academics from computer science who are doing robotics. So we're all mixing together. And as strange as it sounds with the way things are going with remote work and all that sort of thing, being physically co-located is actually crucial, I think, for these kinds of collaborations. And so it makes sense then that we have the robotics researchers from computer science and mechanical working together. So I'd say those are the main things. In terms of the collaborations between the four of us, I guess Phan and Leo have talked a little bit about collaborating, but I'd have to defer to them. But I think generally we try to collaborate with companies because we're quite focused on how things are going to be built in the real world and real world problems, which I think is kind of how engineers work. We find a problem and we're trying to find the solution. That's what we do. And also trying to collaborate with other industry leaders and other academic leaders in the area. So I would say does that answer your question? Hopefully.
Yes.
Okay, good.
Yeah.
Just checking.
Thank you.
Does anyone else Phan, do you want to jump in on that?
I can add on. I think collaboration with people who bring different skill sets is very important. For our field, we have sensor and we can collect a lot of data, but we don't leave the data there. We need someone else to analyze. So working with AI Institute is the key here to make data meaningful. For example, go back to the acoustic sensor again. We work on another disease, the light ring cancer. So many patients who have light ring cancer cannot speak, but they still have the vocal cord vibration. So without sensor, we can attach it on throat, and then it can measure the vibration pattern. And then we work with people from AI Institute, and then they do machine learning, and then they can correlate the vibration pattern with the word that the patient wants to generate. So that a way we can use wearable sensor to support patient with light ring cancer to talk again, or can use that to do daily activity support. You can use the signal obtained from the vibration, send to the robot, and then the robot can do the housework for you. So that's powerful of the blend between hardware and then software. In terms of collaboration between sensor and robotics, I think it's a powerful area because especially after the COVID, we have a lot of symptoms and disease. And one of those is you may heard about edema. Have you heard about edema disease? That you have fluidic buildup in your thighs, and then you need to apply compressive therapy to relieve the fluid. And it's where what Leo is working on as well. So develop compression therapies device that can actively compress the skin and then relieve the fluid from the thighs. And if you apply too much, it will cause discomfort, right? So we need our sensor, pressure sensor, attach on the backside of the compression device, and then provide a closed loop feedback so that it can optimize the compression process.
Thank you. No, I really love the sort of altruistic applications, so that's fantastic. And of course, if anybody here, I know that there's not a lot of time after this session, but if anybody here, has thoughts or want to meet them, of course, please go up to them and talk about collaboration. Or so how does sort of recruitment for the AI Institute work? How do you take on new researchers and collaboration?
So I guess I'm going to answer that question in a roundabout way. I hope that's okay. So we, as I said, we work a lot with industry, and so a lot of the demand comes from industry. And so for the AI Institute in particular, it's academics at UNSW that we work together with. But it is meant to be also a front door for AI at UNSW. So you come to us and you say, here's my problem. I'm working in industry. I have this data lake of stuff that I don't know what to do with, like Phan was saying. Can you help? I'm drowning in data. And so that is a prime example of, you come to the front door of the AI Institute and we put you in touch with the right people in data science, the right people in computer science who can help you to make sense of all that. And so that is a crucial part of what the Institute does, is trying to put together industry with the right researcher, because it can be really daunting looking at a university's webpage, trying to figure out who to talk to, what to say, how do I get in touch with them. And so the AI Institute is this universal front door for that kind of activity. And it's worth saying that we've already had several collaborations with companies we work. So as I said, I'm a underwater robotics. There's a surface robotics company that creates unmanned or uncrewed surface vehicles called Oceus. They have been working with UNSW for years, and we are working with them on trying to help them understand all the data they get back from they've got 5 or 10 uncrewed vehicles that try to circumnavigate Australia to look out for to issues in the seas. And so they have this huge amount of data coming in, and we have already had a couple of successful projects helping them make sense of all that and trying to reduce the operator burden, because they have these operators that are sitting there looking at gigantic screens trying to understand what's happening. So yeah, I think the AI Institute is crucial in bringing that all together, and we're really lucky to have Sue. As you know, Sue is an amazing communicator and amazing at connecting people, which, like I said, is why we're here. So.
Thank you. And I guess finally, before we take some audience questions, I'd like to ask, how much do you currently, and maybe would you like to, collaborate with companies and people outside of Australia? So how much of it is international connections versus just inside of Australia work?
I'll start, but I'm sure everyone's got something to say. International collaborations are what makes academia tick, is what I would say. You can't be a global university like UNSW without working with other global universities. So we had some really constructive discussions today with Keio University. We talked to Tokyo. We're trying to foster, part of our whole reason we're here is to foster collaboration. And it's really important to us as academics that we meet with and talk with people who have fun toys to play with, really expensive equipment we can borrow, but also learn some things from them that we can hopefully take home or work together to build the next amazing thing. Personally, I've got some collaborations with universities in New Zealand and I guess and companies abroad, and we've met with some companies here in Japan too. But I guess, does anyone else want to comment on that one? International collaboration? You want to go?
Just quick 30 seconds, right?
I'll tell you.
All right. Just like international collaboration, mainly my collaborations with universities and some industries in the UK, especially small media enterprise. They just come to us, say, okay, we have these questions, whether you can use your new material, new technology to has at least not fully solve the problem, but have a different angle from different perspective to see whether it's possible to solve this like bottleneck. Because as most of the thing, if it can be solved, it has been solved, to be honest. Just bottlenecks, that's just always, it's gonna be that biggest challenge. There's so many smart people, of course. So what we can provide is just give a different perspective to say, oh, I haven't thought about that. Oh, there's something probably can have some opportunity. That's when I just gradually establishing collaborations. Like, for example, like when I write the grants, I can ask for support from Dyson's, like from all this Robotics Institute. Yeah, they would love to see how this will go, how will solve the problem. If it's not problem, maybe it can make a new product. That's something that I always think about. So yeah, so let's add a few things probably again.
Yeah, just want to add a little bit. One is sometimes collaborating with Australia has some benefits. This is one example. In this trip, we talked with a company, a Japanese company, and we mentioned one possible approach is to fund PhD students to work on a project. And we said in Australia, PhD costs about 40K Australian dollars per year. And our potential collaborator was so surprised when we mentioned this number, because he thought it would cost maybe 100K or something. Actually, it's much, much cheaper than that. So yeah, maybe in some aspects, the cost to collaborate with Australian universities than some other universities might be much lower. So that
the quality is still really high, though, right? It's not
yeah,
just,
of course, of course.
It's spectacular. It's maybe cheap on that, but we still have very good graduates. Yeah.
Yes, yes. Then the second potential benefits. I'm not sure the audience whether they come from industry or university. If for industry, particularly Japanese industry, in the past, some of the foreign industry potential collaborators come to us. They want to collaborate with Australian universities also for the purpose so that they can enter the market in Australia, right? So when you have this connection, when you do some small projects here, and then you understand the market here, you can have some trials here. That could be a possibility to open your market if you want to grow your market to the global. Yeah, that's just 2 points.
Thanks.
My work also heavily involved in international collaboration, especially because I was educated in Japan, so I have very good connection here and still benefits a lot. One of those for our wearable device development, scalable manufacturing is the key. Australia, of course, we have advanced manufacturing, but still behind Japan. So Japan have very strong semiconductor industry. So we are working with AIST, like Sanso Ken, to try manufacture silicon chip at large scale level. That's one example about the benefit of international collaboration. We also have a partnership with a US-based company. And the way we can find the collaboration is based on the principle, everyone work based on their interests. So when we approach them, they never say yes at the beginning if it's not beneficial for the company. So we will always make something that make sure that what we work will benefit the company, or we volunteer. So we ask them, we are more than happy to provide manpower, our undergrads or our thesis student, to explore something that your company interests. And then one example of that is the development of implanted blood pressure sensor into the heart valve. I got donation from Edgeworth Life Science, one of the largest company in the world in making artificial heart valve. And the company have, they make very cool heart valve, selling for $200 per device. But the heart valve have very high rate of failure after fire of implant because they don't have any sensor that can monitor the functionality of the valve. If it blood clot, it will dysfunction. So they want to have a a sensor integrated next to the heart valve that continually measure the thermodynamic behavior. So that's how they approach us. So of course, we work based on the interests, and that's how we build multiple collaborations.
I think that's a key point, is that a lot of the times that we interact, the successful and productive collaborations with industry are often based around a problem. So as Phan was saying, there's a problem that they had difficulty solving internally, and they come to us with a problem. And that kind of problem-based research is what us engineers love, right? Is finding a problem, let me at it. We've got the tools, we've got the people, we can fix it, or we can make a really good stab at trying to fix that. So I think the crucial takeaway, I think, is, especially working with industry, is that it's problem-driven. And so if you have a problem that for some reason is a bit too tricky, then academia is a great way to try and solve that.
Add on that is we have the strength of academic field area is we think outside of the box, so we think unconventionally. Sometimes we provide them very unique solution. Second, we have manpower. We have thousands of students who are willing to work with industry. So sometimes industry interested in some topic, but they don't have resource or manpower to do that. So we are the one who they can connect, and we do it for them.
Well, to wrap up, I just want to say, if you are in industry in Japan, especially a related industry, or if you're connected with any of the universities perhaps here that they have spoken to or that maybe want to speak to them, by all means, make connections with them tonight while they're here. They're on sort of like a fact-finding connection mission. Worst case, if you can't connect with them tonight, please contact the Robotics X Tokyo group or me on LinkedIn. Meet up LinkedIn, and then we'll get you in contact with them. So with that, I'd like to take any questions that the audience might have for the last 8 to 10 minutes or so. And I'll repeat your question to make sure that anyone viewing on live stream can hear. Do we have a live stream? We do, right? I think so. Yes. Yes. Yeah, sure. I just there.
So again, it's been amazing hearing all of you speak. Honestly, it's the sheer amount of brain power. It's just nice to see people. So I work with startup accelerators in Tokyo. We focus on hardware startups, mostly around mobility and robotics. And my question is around the commercialization of the research that comes out of your university. You mentioned a couple of instances where there's some sort of pull relationship where they give you a problem and you kind of like work on the solution, right? But to what extent do you say maybe create solutions or work on, say, frontier kind of issues that do not have clear commercial applicability? And yeah, how does that work in terms of how do you commercialize that? That's all.
That's a good question. I'm just going to repeat the question very quickly. So the question was, you mentioned that there are companies and other organizations that come to you with a problem asking for a solution, but how much is it the other way where you're sort of working on foundational items that you want to commercialize? Yeah.
I will start this, but I'm sure the others have opinions. Thank you for the question. I think commercialization is hard. I think it's really, really hard. Spin-outs from universities are a thing. University really likes to have those because they show real-world impact, and that is, after all, why we're doing engineering, is to have impact. There have been instances of several startups or spin-outs from the university. There's one making fireproof paint. There's another one that deals with hydrogen combustion engines. In terms of robotics, we have one of our current faculty members is doing a startup in terms of agricultural robotics. Trying to solve these problems from taking their research and their projects and taking it out into the real world. The university does have support for that, which is great. There's always this problem of trying to go from having a really great idea to building a prototype is fun and excellent and exciting, and then taking that kind of trough of despair until you get to the real high technology readiness level, which is right at the end there for mass production. But I think we are fortunate at UNSW in particular, because we have a very strong founders group, funding for founders and for startups, accelerators, VC firms are always scouting for opportunities at UNSW. So we're quite fortunate in that way, and to have that ecosystem around us. But it's just so hard, I think is what I would say. Do you guys have thought on that one.
Yeah, I agree with what Will said. I think commercialization is a very challenging thing to do, but at the same time also very important. Why it is challenging? Because you need several factors to work together in order for this to be successful. The first thing is people. Do you have the right people who can drive the commercialization? Many times we as researchers, like professors, we are good at doing fundamental research, but we're not good at translating this into a product. So I do see some successful cases where usually the team, like a student, who either was the main driving force for this technology or getting involved in this technology, but at the same time they have the quality to be a commercialization leader. In that case, we can say successful team where this student become like a CEO of a startup, and then the whole team will be back to support this commercialization. This could be it's a typical case of successful commercialization. Of course, the second important thing is money. Who can invest here, right? At UNSW, we do have this culture. I think UNSW is the best university in Australia to support commercialization. We already mentioned there's a program called the Founders Program, dedicated to support these startup companies, right? Then you bring this investment and the people. Then the next is also, I guess, timing. Right? Whether you can do things fast, quick enough so that you still have a competitive advantage. Sometimes in university, some process is just too long until you get all things sorted and the opportunity already has been gone. So after all these challenges are overcome, then if you can commercialize the technology, that's definitely what you should do, because we as researchers, engineers, we really want what we are working on can become something that's really benefit our society, right? Yeah.
Thank you. I think we just have 1 or 2 minutes left, so do you want to get your question in quickly? Got it. Do you feel like it was sufficiently? Okay. Do you have anything to add about, when you would, make that spin-off? What technology readiness level or?
We're still in academia, so.
Okay, so they're early on.
Would be what I would say, but maybe you have some insight.
Just make it quick. I think that's very good and challenging questions. As academia, we work mostly on fundamental things. So sometimes it's a little bit tricky for us to judge when the technology is ready. But the good thing is about Australia, especially UNSW, is like we have this specific funding scheme called linkage grants. So you can talk to the company, and the company invests a small amount of money, especially SME, and the government match the funding. So you both can explore the potential of this technology, whether it can be transferred into a real-world products. That's just the first stage, called linkage grant. The second stage, you could just go for called AEA grants, which government invests $500,000 1 year, dedicated people, dedicated projects, dedicated efforts, just to make a product. That's what they aimed for. So I think it's really relatively good environment. But as you mentioned, the first thing you figure out is talk to the company, develop the project together. That's the most important thing. You can't just can't work by myself and all of a sudden tell the company, I have this thing, and do you like to work on it? Do you want to buy the patent? No, it's not going to work. I think from my perspective, it has to be right from beginning, develop the things together, and then you will be knowing whether this is feasible or not. Just my opinion.
Thank you very much. Yes, we actually do
that's-
have 1 or 2 more minutes, so you can
Yeah.
throw it in
It's,
there.
we are lucky to have an internal bot that review our pattern applications if it's really feasible to commercialize the technology. So for my group, I work based similar to the way that people pitch on Shark Tank. You have to do market search. The first thing is it has to be problem driven. So that's a need in the market, even something not available in the market, but we believe that people will use. And then we have the industry and innovation team. We can receive mentorship and do market search. What are the total available market time, so on. And then based on that, we will see the feasibility. What are the TIL level, technical readiness level. And if we want to raise from TIL 5 currently to TIL 9, how long it's gonna take? So everything has to be taken into account when we model our business. And that really helpful and give us a rough timeline about the pathway that we can follow for the startup. So, and we have many successful examples which give a very good motivation. One of them, besides the one that Leo's, Will and Shiyang mentioned, is the solar panel. 20 years ago, no one had solar panel, but now it's very common. And if you know that 90% solar panel in the world are built on our UNSW technology. So huge market, and the first billionaire in China is UNSW alumnus in solar panel. So we already have a lot of story. We have ecosystem and the team, industry innovation to support it in commercialization pathway. So we are very confident about that.
Thank you, Mr. Wonderful. Is that the guy from Shark Tank? I actually don't watch Shark Tank, but yeah. And with that, we will wrap things up. Thank you very much to our guests from UNSW. Thank you to everyone for coming and signing up. Please connect with them.
Mike, we have a goodie bag for you.
Thank you.
From UNSW, so Omiyage.
Thank you so much.
Everyone,
I
thank
really
you very much for
appreciate
coming
it.
and having us here.
If it's filled with, chocolates, I will share with everyone.
No,
I
it's
promise.
not.
Okay, sorry.
Thank you very much for
Thank
having
you
us,
very
though.
much. I really appreciate it. Thank you. And thank you, everyone. Have a good night. Thanks.
And we have some UNSW merch here, some pens. If anybody wants a free